Also thanks to the organizers for organizing this workshop and to the audience for being here. As mentioned, my name is Matthijs Ebbens, and I will speak about minimal Delaunay triangulations of hyperbolic surfaces, which is joint work with Hugo Parlier and Gert Vechter. I will start with some preliminaries, then I will introduce the main problem, so Delaunay triangulations on hyperbolic surfaces, and then there will be essentially 3 results. So the first one will give a linear upper bound for the number of vertices of the Delaunay triangulations on hyperbolic surfaces. Then secondly, I'll construct a family of surfaces that actually attains this bound. And then finally, I will also look at the general lower bound. Well, this one we have already seen many times before, but this is just for completeness. Of course, there are many ways in which you can triangulate a point set, for example, here in the plane. And one way to do it is with a Delaunay triangulation. And there's a special property that a Delaunay triangulation has, is that every circumscribed disk of a triangle does not contain any vertex in its interior. Secondly, so I will look at triangulations on hyperbolic surfaces, and these are 2-dimensional manifolds that are locally isometric to an open subset of the hyperbolic plane that we've also seen already many times before. One special property is that you can divide a hyperbolic surface into 2G minus 2 pairs of bands, where G is the genus of the surface. So for example, in the figure, there a genus 3 surface is shown, which is divided into 4 pairs of bands. So 1 here, 2, 3, 4. And each of these pairs of bands is a topological sphere with 3 boundary components. And because the hyperbolic surface is locally isometric to the hyperbolic plane, this means that the Gaussian curvature is constant -1. And by the Gauss-Bonnet theorem, that means that its area is given by 4 pi times G minus 1. So it's only dependent on the genus and not on the metric. So in this talk, I will focus on distance Delaunay triangulations. And this is a triangulation that is simplicial, that satisfies the Delaunay property, so the empty circle property, and its edges are distance paths. And well, in the triangulation I showed you before, it was already simplicial, because in the plane there are no, well, if you have shortest paths, there are no ways you can get loops or double edges. But of course, on surfaces, you can get double edge or loops. So this is why we exclude it by asking that it's simplicial. So now the main question is, what is the minimal number of vertices of a distance Delaunay triangulation of a hyperbolic surface of genus G? And preferably, we want something that only depends on the genus. So the first result says that for any closed hyperbolic surface of genus G, there is a distance Delaunay triangulation with at most 151 times G vertices. And this constant 151 is, of course, not optimal. And you could probably, this is just some artifact of the proof, but the constant also doesn't really matter that much. It's just the important part is that it's at most linear, a linear function in terms of the genus. For the proof, we need the notion of the injectivity radius of a point on the surface. So given a hyperbolic surface like this one, and given a point on the surface, then the injectivity radius at that point is the radius of the largest embedded open disk at that point, as probably many of you know. And then the injectivity radius of the surface is the minimum of all the injectivity radii. So for example, on this surface, the injectivity radius of a point over here will be larger than of a point over here. The reason that we define this is that we are going to divide our surface into an epsilon thick part and an epsilon thin part. This was also already mentioned earlier today by Christopher Bishop. And the way we do that is we fix some parameter epsilon, usually quite small. And we look, so the epsilon thick part is the part of the surface consisting of all points which have injectivity radius at least epsilon, and the epsilon thin part is the complement, so all the points that have injectivity radius at most epsilon. So in this case, for example, the epsilon thin part would be the shaded red areas, and the rest of the surface is the epsilon thick part. So now the proof for the upper bounds of the number of vertices goes as follows. So first, suppose that there is no epsilon fin part. And remember that throughout this whole story, our epsilon is fixed. Then we are going to construct a maximal packing of this surface with disks of radius 1/4 epsilon. And you can show that actually, so then we are going to look at the point set consisting of the centers of all these disks. And you can show that the set of points consisting of all these centers is the vertex set of a distance Delaunay triangulation. So the only thing that we need to do is give a bounds on the cardinality of this point set. Well, each of these disks, so it has radius 1/4 epsilon. So in hyperbolic geometry, that means that its area is given by this expression. And we also know that the area of the hyperbolic surface was 4 pi times g minus 1. So the maximal number of vertices that we can get is bounded above by the number of disks that we can possibly fit in this surface, which is just our quotient. And because our epsilon is fixed, this will give a linear number of vertices. Then secondly, suppose that there are some fin parts. Then, well, already the figure suggests a bit that this part will look like cylinders, and in fact it does. So if we take epsilon sufficiently small, then it's guaranteed that the epsilon fin part will consist of a collection of cylinders. And that's nice because cylinders are quite easy to triangulate. So each of these cylinders will be a so-called collar around a geodesic gamma, and it has two boundary geodesics, gamma minus and gamma plus. And to triangulate we can just put 3 points on the two boundary curves and 3 points on the geodesic in the center, and form a triangulation like this. And you can show that this is a Delaunay triangulation. Also, when we start adding points later on to the rest of the surface. And so these are 9 points for one cylinder, and it's also known that there are at most 3g minus 3 of these cylinders, so at most 27g minus 27 vertices. So something linear in the genus, which is good. So how are we going to make a triangulation of the entire surface? So first we are going to treat the cylinders separately, as I showed before. So we just place the 9 points in each cylinder. And then we are going to triangulate, well, to form a circle packing of the rest of the surface as we did before. And again, you can show that the vertex sets from this construction has a distance Delaunay triangulation of the surface. And for each part, we have shown that it's linear. And if you start working out all the constants and take a nice epsilon, you will get the 151. So now you can ask whether how good is this linear bound? Is it close to optimal or not? And so the next result says that there exists some constant b, maybe small, or probably small, that depends on some parameters a and b that I'm going to define in a minute, such that any minimal distance Delaunay triangulation of a hyperbolic surface in some set of surfaces SJB that I'm also going to define has at least b times g vertices. So what are these surfaces? As I mentioned, you can decompose a surface into pairs of pans, but you can also do the reverse. So you can start with pairs of pans, glue them together and get a surface. So a way to describe or to construct hyperbolic surfaces is to describe how the pairs of pans look like and how you glue them together. Well, as I mentioned, a pair of pans is a topological sphere with 3 boundary components, say with length L1, L2, and L3. And now suppose that we take these lengths in some bounded interval AB. And these will be our parameters A and B. And it's known that for hyperbolic pairs of pans, these 3 boundary lengths completely determine the geometry of this pair of pans. And well, then we will glue them together in this way, so to speak, they are all in a line. And well, there are no deep reasons for this. This is just to make it easier well, for bookkeeping and to check where are the vertices and where are no vertices. And well, if you glue 2g minus 2 of these pairs of pans together, you will get a genus G surface. So the set SGAB will consist of all the surfaces of genus G that you can get by pasting together pairs of pens with lengths in A in this interval AB. And so the theorem says that there is some constant B depending only on these parameters A and B and not on the genus or whatever, such that we have a linear number of vertices. So I'm just going to give a sketch of the proof. And if we can show that the number of edges is at most linear in terms of the number of vertices, then Euler's formula shows that the number of vertices has a lower bound in terms of the a linear lower bound in terms of the genus. So that means we need to find a linear upper bound for the number of edges. So to do this, first suppose that there exists some DDT of our surface which has asymptotically strictly less than G vertices. As I mentioned, there are 2G minus 2 pairs of pens. So if there are strictly less than G vertices, that means that a lot of these pairs of pens do not have any vertices, actually. So it sort of looks like this. You have a pair of pens which has some vertices, or maybe a few. Then there are a lot of pairs of pens that don't have any vertices, and then again one or a few that have some vertices, and so on. But now observe the following. Suppose that we have a vertex in some pair of pens, and it has an edge going to another vertex in a different pair of pens, and this edge crosses a lot of pairs of pens in between. If this is an edge in a Delaunay triangulation, that means that there is an empty disk going through these vertices. So this disk does not contain any vertices in its interior. Well, you can sort of imagine that if there's a disk going through these two vertices, then probably the two pairs of pens in the center will be completely covered by this disk. So there will be no vertices in these pairs of pens. So if we go back to our image of the triangulation in general, suppose that there is some edge going from a vertex from here to the rightmost pair of pens. Then by the previous observation, that means that probably this one should be empty. This one should be covered by the disk going through these two vertices. But if there are vertices, that's not possible. So the conclusion is that this edge is just not possible. And of course, there are some details here to work out, but essentially the result is that you can decompose the surface into sort of blocks where, so for example, here's a block, and the only edges that are, the edges will always go from a block to itself or from a block to the next block. But there will be no edges going from a block, then skipping one and then going to the next one. And well, again, there are some technicalities here, but using this approach, using that there are a lot of edges that just cannot be included, you can show that the number of edges is linear as a function of the number of vertices. And as I mentioned by Euler, that means that the number of vertices is at least linear. So then finally, is this linear lower bound, does it hold for all surfaces? Well, to give an answer to that question, we are going to sort of take a step back and look at a more general problem, namely simplicial triangulations of topological surface. So no metric anymore. And it was shown over 40 years ago that you need at least something on the order of square root of G vertices to make such a triangulation. So of course, also you need this many vertices for a distance Delaunay triangulation of a hyperbolic surface, because it's even more specific. But in fact, you can construct hyperbolic surfaces for infinitely many genera that have actually a distance Delaunay triangulation with exactly this number of vertices. So you don't lose any, you don't need any more vertices in these. Unfortunately, it's not for every genus, but still. And the idea of the proof is as follows. So suppose you have some n divisible by 12, and n will be eventually the number of vertices. Then we can define our genus as this expression, because when you solve that for n, you will get exactly the right number of vertices. And then it is known that there exists an embedding of the complete graph on n vertices into a topological surface of genus Gn. And the nice part is all faces are triangles in this embedding. And well, that's good for us because we are looking at triangulations. So we just replace every triangle by a hyperbolic triangle, and we make them equilateral triangles. And also we choose the angle correctly so that in the end we end up with a smooth surface. And this way you can form distance Delaunay triangulations of these hyperbolic surfaces. So to summarize, we've looked at distance Delaunay, well, the number of vertices of distance Delaunay triangulations of hyperbolic surfaces. And we have shown that you need at most 151 times G vertices. For some families of surfaces, BG vertices are needed. But there are also some surfaces that need at least square root of G, or well, for which square root of G vertices are sufficient. Well, thank you for your attention. If there are any questions, feel free to ask.
All right, thank you. We have time for some questions.
So I had a question about the example with the square root estimate. So you're putting each vertex is then in a lot of triangles around the square root of n triangles, I guess. What's the thick, thin part? I mean, can you describe what that surface looks like? Does that have, are there these, is it like completely thick, or are there thin pieces, you know, at each vertex? Is this sort of a strange looking Riemann surface in some sense, or can you say anything about the thick, thin pieces of that?
That's a good question, because I also try to visualize what it should look like. So indeed, you have a lot of triangles around each vertex, because, well, there are, it's a complete graph. So you have these n-1 triangles coming together at each vertex. This is also why you make the angles all equal and making all the triangles equilateral. But I couldn't form an image of what it would look like in terms of the thick fin decomposition. Mm-hmm. It's sort of, it looks like the injectivity radius of the surface of the surface, like of the entire surface, would be quite large, but I didn't find a proof.
Okay. Is this a surface with a lot of symmetries? I mean, is this complete graph sort of acting on it in some way, or not particularly?
Yeah. Well, all the triangles are equal, so you can just move all the points to each other.
Mm-hmm. Yeah, well, that must be a very unusual surface then.
Yes.
So there is a some kind of bound. I forget the details, but there is some kind of bound on the automorphism group that can act on the genus G surface. It's bounded by what, like something like 84 times the genus, and perhaps that tells you something about what this thing has to look like.
Yes. Yeah. So for me, the hard part in visualizing these kind of things is that indeed there is an upper bound for the automorphism group, and I think it's indeed linear, something like 84.
Yes.
No, 48, yeah, G-1, something like that. But in terms of, like, for example, thick fin decomposition, I'm not sure if it says anything about that. And combining the two sort of images seems harder, at least to me. I don't really have an intuition for how it would work.
Okay. Well, it seems like it would be a fun thing to try to figure out, at least when these numbers were fairly small.
Yeah.
Okay, thank you.
It's a question.
Aaron, you have a question?
Yeah, thanks, Matthijs, for the talk. So I guess you have examples of families, right, where you have square roots of G, and you have examples where you have G. I guess sort of what should one expect generically? I mean, if you want, we can fix a nice measure on moduli space and then ask what the sort of the expected distribution is with respect to that, or like you sort of had you had a different schema for triangulating the thick parts and the thin parts, and you can get bounds on the volumes of the thin parts in moduli space. So like, can you say anything about like what a generic surface is like?
Yeah, I cannot say anything definitely, but my guess would be that it's more towards the G, the order G, because so the example I had shows that essentially given any surface, you can form this BG. The only problem is that so going back to that, so this one. So essentially, you can create any surface with this, but it just you have to choose the right A and B, and then your constant B depends on these A and B. So this makes it a bit tricky to see what happens in general. It could be that there is some sort of continuum between this square root of G and the linear G, and that maybe there are some surfaces that are in between. And then it would sort of have to do with like the influence of this A and B on B would sort of give a dependence of B on A and B, and this would, for example, how to say this? The problem is when your genus goes off to infinity, you'll get your surfaces might grow small. The injectivity radius might go smaller and smaller, and this might lead to your A going smaller and smaller, and your B going smaller as well, and then you would need maybe more vertices, less vertices. But indeed, I'm not completely sure. So to answer your question, I'm not completely sure what happens for a generic surface.
Can I actually ask about the statement of this theorem? Sorry. Just this theorem is for like for any B, right? You have a constant so that you have at least PG vertices sort of as G goes to infinity, right? Like
yes.
Okay.
So one way of looking at it, so to add one thing, there is some work on looking at random surfaces, and one of the things that were shown there is that when you take a random surface in some sort of when you take an appropriate probability measure on the space of surfaces, then the injectivity radius will be bounded below by some constants, and that would mean that this A should be bounded below by some constants. And what it exactly means for this is not entirely clear, because they're still dependent on the little b. But it suggests that maybe it goes towards the G number of G vertices.
This is Chris again. Just one observation is that you have this lower and upper bound on the lengths of the pairs of pants, but probably the lower bound is not so critical, because when you have a pair of pants that has a short collar, that means that the leg is very long. So if you were to make L1 here smaller, the length of that trouser length would be getting longer and longer. And so if the L's, the L1, L2, and L3 are all small, the boundary components are far apart from each other. And then your proof of lining them up in a row works fine. And the smaller the L's are, the further apart the blocks are, so everything is okay. But when the L's are big, then those loops become closer together. And so when you have L's which are large, then you can stack 1,000 pairs of pants all together, and they're only about unit distance apart. And so your blocks are all squashed together, and then your argument doesn't work so well, that the middle blocks have to be avoided. So I would suspect in your thing, you really only need a bound on the upper bound of the L's, not a lower bound.
Indeed, that's a good observation. One reason why I need this lower bound A in this proof is, well, so the proof makes use of it, and it uses it over here.
Yes.
Because when this A and B fix the geometry, and this also means that when you look, for example, at the diameter of a pair of pens, it's also fixed by the A and B, but also the distance from one boundary geodesic to another. Right. And this one sort of gives a bound on the number of pairs of pens that might possibly still contain some vertices. So in the proof, so this one was a bit simplified, of course, but it has something like, there is some constant n depending on each A and B, and the first n pair of pens may contain some vertices, and the last n as well, but then everything in the middle is empty.
All right.
So in this case, well, it would be the first one.
Well, I may be biased by my own thoughts on Riemann surfaces, and the problems I've thought about or trying to understand papers are interesting classes of surfaces in which there are no short loops, in which all the loops are fairly long. And in that case, the enemy is when the pairs of pants all have long hems. It's difficult to understand, but a very interesting talk. Thank you.
Yeah. Thank you.
All right, thank you. Well, let's thank Matthijs one more time. Thank you. And all of our speakers for today. The